Good morning and welcome. And this was yesterday, so it was a little bit busy, and we had something really cool in the afternoon. We had hackers versus suits on a panel, and the questions were highly amusing, and the good news is for you guys, the hackers won. Anyway, so there seems to be a bit of discourse about who we actually are, the people who run 44Con. And this was in SC Magazine in April. So just so you're clear about this, I am the mysterious Adrian, and the mysterious Steve is upstairs, and he's the one limping. There will be something in my clothes tomorrow about said limping, and about my limping, and another crew's limping, because this really is turning into CrippleCon. But yeah, c'est la vie, c'est la vie. Anyway, the last talk yesterday was Jason, and he kicked ass, and this action photo tells you what he really got up to. And we did actually run yesterday to time. And the reason for running to time was this little baby called the Nerfulator 3000. And if you look here on the left of the stage, you see it does actually have quite a good range of movement. So don't think it's just me that's going to get shot, or a speaker that goes over their allotted time that gets shot. And the way we do it is, the speaker gets 1 or 2 warning shots, and if they continue to take the proverbial, then it's got something rather more interesting. It's got a second firing mode, which you'll definitely see today. Definitely see today. So we've got the talks. What else do we have? For those of you that weren't here yesterday, we have upstairs the Blackberry Lounge. So that's in the Sentosa suite. You go through all the exhibitors, and it's in the far right corner. We got complaints last year that tea and coffee, the breaks were too short, and there weren't enough of them. So as part of the condition of coming here, we said, right, we want tea and coffee running all day. So you want a coffee at 8, registration, you can have one. You want a coffee at 5 in the afternoon, you can have one. It really doesn't matter. There is a cash bar where there is Guinness, very good Guinness from a keg, and we had no complaints yesterday from certain security professionals who tested it really a lot. But of course, as this is 44Con, we've got other things that happen. So on your program, you'll see a thing called Gin O'Clock, and that happens around 3:30, I think. So make sure you're up in that area at 3:30, because very nice things will happen. You know, you're an English con. Gin and tonic is a reasonable thing to drink, right? Yeah. So anyway, again, because we're 44Con, we do something a bit special. There's free beer from 2 o'clock. The trick is you have to go and talk to some of the sponsors and exhibitors to get said free beer. Please do this, and really please spend time talking to them, because otherwise your ticket price would probably be triple what it actually was. We rely on them to subsidize the cost of the whole con. If you partake of the evil weed, then we have a smoking area for you. Go up to the Blackberry Lounge, and then you'll see some doors that go into a courtyard. You can smoke there, and you can take your drink out with you. So if the weather's nice, it should be okay. And really, you know, one thing that's associated with that area is networking. This is one of the main reasons we ran this event, because, you know, certain other events are good for people who are in the vendor land. There really weren't that many events for people who actually did the security stuff. So that's why we're here. And to help socialize, we have a visitor from across the pond who specializes in these things called awkward hugs. And they're not painful, I can assure you. I survived mine. And we have a little wall of awkward hug, and there is a domain called awkwardhugs.org where pics will appear. And Jason does travel the world to security cons, and the awkward hug is one of the things that both, you know, advertises the con a little bit, but also adds to his awesome personal brand, which we love. So, there's already so much to do. We've got a bit more. There's a CTF competition. You register on the front desk, And a member of Ops will come down and take your team registration details, and you'll be, it goes soon. The format of the CTF is in your brochure, but basically it's an attack-defend scenario. You've got to defend a VM, and you can attack other people's VM. There's a scoring system, and there are rather a lot of very nice prizes. I think we've got 4 or 5 teams in there from yesterday. No one's got a huge lead, so I think it could be quite fun. Oh gosh, there's even more to do, sorry. There's a crypto challenge as well. It's in your brochure, but on the way to the printers, some of the pixies took out bits of the crypt, and they scattered them all around the venue, literally all round. Make sure you look high and you look low. They look like little white bits of hex, and you slot those into the right bit of the string. We've got Wi-Fi. 44Con Secure is as good as it can get. Pick up random usernames and password from reception. We don't track you, we don't care what you do, though please don't take the proverbial. If you're doing the CTF, you've got 2 choices. You can go on the Wi-Fi CTF network. I suggest if you don't know what CTF is, you don't go on that. Oh no, that'll be that. But there's also wired connections to the CTF, and I think I've got a slide about that later, but that's up in the BlackBerry Lounge as well. We've got some 44Con goodies, some lovely mugs, we've got t-shirts and some really quite awesome bags. So please, we need you to buy these things. And then there's something else. Again, it's 44Con, we've got so much going on. You can't possibly see all the talks. You just can't do it. So if you look here, we have the good Eric from Source of Knowledge, who do all the DVDs for Black Hat and DEF CON, and they're about, what, $400 or $500. This is 44Con with a reasonable price con. Our DVDs are 50 quid, and you get every single talk from all 3 days, except for 2. The panel yesterday we couldn't record because 2 of the people on the panel could not get a legal release from their employers to be there, and we really would like them to keep their jobs. And there was one talk yesterday which had some interesting stuff in, and you had to be there to see it, but c'est la vie. I think all talks today are being recorded, aren't they? Yeah, so don't worry if you sat doing the CTF and the crypto challenge and networking in the bar. Just go to reception. It's £50, but you have to order while here at the event. We need to get 1 production run done and dusted for that price. We will sell them later, I don't know when, and it will be more than £50. So we take cash, credit card, sons, daughters, bits of legs. We've got some more things with 44Con happening. We've got 44 Cafe again next year in April. We were meant to be doing the 44Con cycle ride on the Olympic cycle route, but as some of you may have heard, I had a little incident last week. I'm seeing my physio today. He's coming here to the venue. That should be fun. And I'm seeing my osteo on Saturday. We're trying to figure out what's wrong with my ankle. More fun things. We've got a little party for you. MWR are doing a massive event. Be here for the last talk, which is Dan Cuthbert and Glenn of SensePost. And after that talk, you'll be following the directions of the crew and security guards back over to the other building, and you'll be sent up some steps to another room. Have fun. It's going to be an awesome night. Ow. So, one last thing. It's the nature of a con. We have to move things round because things happen. So, if you wanted to see the 4G testing talk that was meant to be in Orchard 2 at 12 o'clock, it's now going to be in here at 2 o'clock. We've got a new talk that's going to be in that original slot at Orchard 2, and Chris Sumner is going to treat you to a bit of psychopathy on Twitter. I think we all know people that display those issues. And then there's a workshop change. To really tie in with Phil's talk, we've moved his workshop from yesterday to today, from tomorrow to today. So he will be showing you how to create fake USB devices in workshop 1 at 2 o'clock. So just to be sure, we're recording everything in Orchard 1 and Orchard 2. We're not recording anything in the workshops, and we're not recording anything in the demo area or anywhere else in the con. So, enjoy. Hope you learn a lot. Hope you have a lot of fun. We do need to know what you like. We need to know what you don't like. It's giving us the feedback helps us improve and make the following year better. And thank you so much for coming, because without you, we wouldn't be here. Have a great day.
Okay, so this talk's been given a number of different titles: Post-Exploitation 2.0, Modern Post-Exploitation Strategies, the keywords post-exploitation, whatever's around it, it doesn't really matter. This is what we're going to talk about today, or if you were out last night, this is what we're going to talk about today. So who am I? My name's Rich Smith. I currently work at Kairos. I lead the attack technology team there. Previously, I've worked at Immunity as a senior researcher. I led the research in offensive technologies and threats at Hewlett-Packard Labs for 6 years. I worked at Morgan Stanley as a vice president most recently, which is hilarious, and led their CERT team for a short time. So basically this slide is, why did you haul ass out of bed at 9 a.m.? Hopefully this kind of gives some credentials that I might know something about what I'm talking about. And what are we going to talk about? So I'm going to talk about I'm doing some ongoing research and extending techniques in pen testing, in attacks, for the long-term engagements which we do for our customers. Now these are slightly different than many people may think of as kind of traditional pen tests. They're much longer term, they're generally more complex and multi-step. And so all the workflows and the proof of concept tools that we're going to have a look at today, they all came from kind of the real world needs that I saw for solving the problems for our customers, and the shortcomings in the tool sets which were generally available. And so this, that's kind of the basis for this talk. There was a big shortcoming in a lot of the available tools in the area of post-exploitation, and hopefully there's some fodder to think about this morning. So some of the things that we're going to look at, attack process, attack workflow, how tools currently map to these workflows or don't, as the case may be, and really this difference between pen test versus attack. I'm not sure how many of you were around for some of the talks that were given yesterday, but there was some talks that really spoke very clearly to that last point. What is that difference between kind of red teaming, attack teaming, specifically targeted attacks, whatever you want to call it, the difference between pen test and those, and the values the different values you get from both of them. I'm going to touch on that, but my main area is going to be kind of attack process, attack workflow, and how we're probably selling ourselves short with a lot of the tooling which is available. So one of the things that I do, I attack a lot of people. It's my job. That's what I'm paid for. And we perform highly targeted attacks against our customers. So this isn't like running a web app scanner against an application and saying, yeah, there's some XSS here, there's a SQL injection there. This is long, ongoing engagements. Think 6-12 months, not 6-12 days. And we generally work in a goal-driven manner, which is high-level goals. So we're not going to be finding XSS in a specific web application. We're going to be given a goal like read my CEO's email, or alter the source code. We're the development company. I want you to get right access to our source code repository. This is our high-level goal. How we achieve it, all the steps that we string together to get to these goals, that's what we do for the customer, and we help educate them as how lots of maybe smaller vulnerabilities that may not seem have a huge impact on themselves can really be strung together and have these major impacts that are meaningful to that customer. So this is kind of the area which I'm focusing on from my attack. So this is long-term, multi-stage, incremental attacks. It may take 6 months before we even get near one of those goals, and we just going to roll on, take the opportunities as they arrive. If there was a system that we found that we didn't understand enough, research that system. Custom exploit development. We'll do vulnerability research. Whatever it takes to kind of get there and do these complex attacks for customers, so they can really feel what it's like to be under a specifically targeted attack, which they may well be in the real world. Now, obviously, for a lot of the customers that we deal with, they're pretty mature in their security anyway. I'm not sure I mentioned on the first slide, so with Kairos, we're based out of DC. I work out of New York, but a lot of our customers are in that Beltway area, so they're pretty mature with their security model anyway. And trying to do this level of attack with the tooling that's out there, really found that the tooling currently fell far short. It just wasn't up to doing complex attacks. It was fine for pen test, for illustrating there was a technical problem, a specific technical problem, but it wasn't great for really then taking all those next steps that follow from that. I love this picture, but the best part, the kid in the back, he's just like, sucking on his ice lolly as his friend's going to be castrated. It's awesome. So I really feel quite strongly, my passion is tooling and framework design, and really trying to do that in the best possible way for attack tooling. And I feel a lot of the current tooling really falls short. I think a lot of the current tooling is produced for conferences such as this, to show off an idea. It shows off that idea well, but it's never necessarily maintained that well. It's never linked into a bigger workflow. And for doing complex attacks, it really isn't suitable for purpose. And so kind of the easiest way that I can try and demonstrate this, recon, so things like Multigo, fantastic for doing full surface recon, both technical assets and like meat space assets. Your people, your HR processes, all that kind of thing. And so you recon out, you get your attack surface, find out all the resources which are available to you to aid you in your attack. And then you exploit one of them or more of them or many of them. And that exploit, it's momentary. It's very difficult. I'm not underselling the difficulty of exploitation. I've spent a lot of my career doing vulnerability research and exploit dev and exploit weaponization. But in the whole timeline of an attack, when you look at an attack in a step back, full process way, an exploit is really the start of the attack. And then you've got this whole area to the right, which is essentially the post-exploitation process. What do you do after you get onto that box? All the areas to the right, often very not well explored. The exploitation area, because it's cool and it's sexy, people spend hours and hours and many, many talks. You go to Black Hat, a vast majority of talks will be around, kind of in the attack space, will be around exploitation, not post-exploitation. How do you do complex things after you've got access to a system? So, I've thrown around this post-exploitation word a lot, and I've got obviously no idea where people in the room are. You could all be seasoned pen testers, or you could be information security managers that have got no idea what I'm talking about. So what is post-exploitation? It's what you do after the compromise. It's nothing to do with how you compromise. So nothing that we talk about today is going to be how to get on the box. We're just assuming that you're on the box. And then what do you do afterwards? A different way of looking at it, maybe from an attacker's perspective, is how do I make the best use of systems that I've compromised? I've spent all this time, I've done vulnerability research, I've developed an exploit, it's landed, I've got a point of presence on that box, how do I make the best use of it? So as an attacker, what do I worry about at night? What keeps me awake? What are all the things that I kind of give me a sleepless night that I need to do better, that I worry about is going to be affecting my attacks that are ongoing for 6 to 12 months. So obviously this is an attacker, you can tell that because he's in black. And he has a target. That target, he needs to gain access to it, he exploits it. You can tell it's exploited because it's got skull and crossbones on it, the universal sign of both hackers and pirates. So what's the first problem? Well, obviously the exploitation, but we're talking about post-exploitation. So we assume that just happens magically. So we've got this exploit, remote, ring 0, O-day, whatever, doesn't matter. We've got a point of presence. Now as an attacker, I need to gain persistence onto that system. I need to have a backdoor, a Trojan, an implant, whatever you want to term it. I've backdoored the system. And inherently, by me having that persistence to regain access to that system, I'm more likely to be detected. So my first worry is, how do I gain persistence? My next worry is that persistence being detected. Is anyone going to detect my little pony on there? And then my next problem is, right, well, I'm not just doing a single system. I'm attacking a whole corporation, and maybe a multinational corporation with these high-level goals in mind. So I'm going to have to attack, maybe 3, maybe 5, maybe 30, maybe 3,000 systems. How do I do that in a scalable way? How do I get my horse on all of those systems? Scalability, software engineering problems. Then we add in like a mix of different operating systems, and now that means every single pony has to be a different pony because it has to be specific to that system. Now I've got software engineering problems of just scaling my development team. I'm running a team of people, and I've got to make sure that both my exploits land, and then all my post-exploitation tooling works across a variety of different platforms, a variety of different OSs, and now a variety of different devices. So a different way, every worry can be turned around to be a challenge. So if we look at the high-level challenges that I see in post-exploitation, doing complex attack, I want to avoid detection, for fairly obvious reasons. I want to avoid, there's a whole industry that's AV and who are tasked to find my ponies. They probably would term it in slightly grander detail, but they're looking for my pony. I want to manage many, many targets in a scalable way. I may want to manage 3,000 targets across a corporation, across multiple different geographic sites. I also want to allow my attack team to have rapid development. So this comes back to that problem of having very platform-specific post-exploitation tooling, where I have to, if I want to search a hard disk for a particular document, I don't want to have that payload be different for every single possible platform that I may encounter. It's a software engineering nightmare. And I also want to be able to, when I come across a new system, rapidly be able to write up something to work against that system. This is what high-level languages, and there's a lot of just general purpose software engineering that they've got a really good handle on. And in the post-exploitation world and the attack tooling world, we really haven't. People are still writing things in C. There's a lot of very low-level languages that are used that aren't good for rapid development. And then QA and maintenance. This is it was the last point, but it really is quite important. I don't want to be crashing boxes, and because operating systems and versions and patch and language patched all coming out very rapidly, to be able to regression test any sets of capabilities which I have across all platforms. Again, software engineering nightmare. There's a lot of well-tested solutions for that, but they're not really being used in the attack space. So one other worry that I really have is technology futures. And how will they affect how I can attack things? And I'm not just talking about new defenses that come up. I mean, obviously, I lose sleep over those, and how can I avoid them? But just general changes in how people are using technology. And probably the best discussion I've seen of this recently, I'm sure you've all seen this, is the Gartner hype cycle. And it's got pretty much every buzzword that you can imagine on there, placed on this arbitrary curve, and then it's got areas like the trough of disillusionment and the slope of enlightenment. It's awesome. It's like Lord of the Rings meets American Psycho. And so I'm not really worried about where these things are on that curve. The questions that I'm asking myself when I see that curve and all those terms, and you've all been bombarded with a million Slashdot articles about cloud computing and bring your own device and all this kind of stuff. What do I think about in my attack sense? Well, how is it going to change the effectiveness of my attack? Something which I may be counting on or have counted on as just a given paradigm for computing. Some of the things like cloud computing are really shifting those paradigms. How will it change my effectiveness? How will it affect the cost of my attack? For me to launch a successful attack, gain persistence, avoid detection, all of those things, are these things going to push my cost up, or am I going to be able to use some of those technologies to my advantage as an attacker? And from your side of the fence, when you're looking to defend against these things, I think that's a question that you probably should be asking yourself. Is the utility of these new technologies? How does it change my attack surface? And does it create new targets? Does it shift the target of where me as an attacker will be focusing against your corporation because you've employed a new paradigm? So don't necessarily focus on the defenses, the new defense technologies which come out, but just the general computing landscape. The attack landscape will change to reflect the changing technology landscape. I think a lot of people feel that the technology landscape is being driven by the threat landscape. I personally don't. I think the threat landscape is inherently reactive. So some of the paradigm shifting trends that we all hear about, cloud computing really is shifting your attack surface, because you're pushing processing and data obviously out into the cloud. You don't necessarily own those the computers where the processing is happening. There's a lot of shifts there, and it really does change your attack model. Mobile devices. So obviously, everyone's heard about lost and stolen mobile devices. The security which is inherent in some devices and not in others. They really do open up obviously a whole slew of different attack opportunities and also attack challenges. Now a lot of people I can see just sitting on the front row. They're all using iPads. 5 years ago, everyone would have been on a laptop. Oh, sorry, an Android tablet. I'm sorry. So you can see which fanboy I am. So bring your own device. I think there's a good conversation around this of, is this actually happening? There seems to be a good push from corporations for it to happening, because they can just see that they can reduce their expenditure on equipment. There's actually quite a good push from users, because they don't want to use the crappy Toshiba laptop. I hope no one from Toshiba's in the room. That they were issued by the IT guys. They want to use their Android pad. the bringing your own device phenomenon really changes the dynamic of what you can achieve as a security team. Where does your policy reach to in these new devices? What can and can't you enforce? There's a lot of them privacy regulations and all the European Union stuff. So again, changing your attack model, changing the technology landscape, which changes my attack model. And obviously social media, I'm sure people are tweeting as we speak, like, why did I get up at 9 a.m. for this? But social media really, changing the kind of the divide between technology and kind of real life meet space, and merging those together in ways that it's never been done before. So the overall trends as an attacker, from an attacker's point of view, there's a larger number of resources for me to attack than ever before, and that becomes problematic just because there's so many of them. And there's a greater diversity in those resources than ever before. It used to be a pretty safe bet that you were going to be on an x86 box that was running some variant of Windows. It was a pretty safe bet. You could put your eggs in that basket. You could tool up against that, and you could get into kind of most targets. With the advent of mobile devices, there's different chip architectures, there's different operating systems. There's just a bigger mix. And so, if we think back to that, the picture with all those ponies, and there was only 3 ponies there, and it was like the mix of the standard desktop operating environments. But actually, when we start to mix in all these different devices, it becomes a very difficult challenge for an attacker to have, very reliable, scalable attack. And there's much more inter-resource complexity than there ever has been before, and that really is kind of this kind of like cloud drive, and things are relying on discrete services that are being provided, and this deeper relationship between users and technology than there's ever been before. So social engineering really does become, a very key factor in any large-scale complex attack. So if we kind of believe these trends, and then we look back at these challenges, and then we ask ourselves, kind of like, well, all these things, all those challenges, all those trends, how are we doing? How's current tooling doing? Well, we're back to the kid that's about to never have kids. So the 2 areas that I'm really going to focus on, and there's a lot of areas within tooling that I feel fall short, but that's going to feel like a whole day's worth of me standing up and bitching. I'm going to focus on 2 for this morning to save your ears. I'm going to address poor scalability. And the current ways that post-exploitation is done, which is essentially a binary dropper. You exploit a system, it uploads a binary to the target system, and then you interact with that target system via the binary. It just doesn't scale. It doesn't scale well in the development process for my guys who are guys on my team when we're writing new capabilities, and we have to develop them in a low-level language and push them out and test them across all these different devices, all these different targets which we may want to attack. It just doesn't scale. Reduces my ability to be effective against a diverse target set, which when we're looking at complex attacks really is key. I want to be, I don't want to be saying I can only attack this subsection of the company's infrastructure because that's the only thing I've got capabilities for. And vast majority, if not all, of pen test frameworks use this binary dropper approach, and it's just a software engineering nightmare if you're trying to use these pen test frameworks in real-world complex attack where you're going to be dealing with a very diverse target set. So, poor scalability and baking in. A lot of people in this binary dropper approach, push over everything that they could possibly want to do on a box ever over to the far side, and it's all there. Now, from a complex attack and from a non-pen test standpoint, baking in your capabilities can really reveal your hand. It can show the intent of your attack, and we saw this incredibly well thought out for Flame and Stuxnet. All the reverse engineers went crazy and just reversed the heck out of it and found everything that could be done possibly. So the guys that it could have been girls, the people that dropped those targeted Trojans, the intent of that attack became very clear because every capability was in the binary, and then it was reversed out. Some very talented guys did all the reversing. So you can just you lose your MO. It can also really reduce your flexibility because I've got to know ahead of time what I want to do on a target, and that's not always the case. I can't know ahead of time exactly what I'm going to do on the target because I won't really know necessarily what that target is until I'm there or what else it's connected to. So reduction in flexibility and really kind of showing my hand if my pony is ever detected, which given a lot of the advances in defenses and the AV guys and all that kind of thing, it's a reasonable chance that things will be detected. So obviously there was a huge amount of media focus on Flame, and And it was huge. It was like 20 megs. And it was like, oh my God, the sky is falling because of this thing that's like 20 megs and it's got an embedded Lua interpreter and blah. Oh my God, it's crazy. Big isn't what worries me. When I was working at Morgan Stanley running their cert, when we had a big malware, it wasn't a problem because I could just throw money at that problem. I could get reversers to tell me who it came from, likely country of origin, was it from a group that we had been hit from before, all these kind of things because we had all that data there. It was small that really worried me. If there was something that gave me no idea about why that was there, what it had done in the past, and what it was there to do in the future, that was what worried me. That was a sophisticated targeted attack, or APT, or whatever three-letter acronym people want to wrap around their marketing for these things. But small is more worrying to me. So, our high-level aims. Excuse me. As an attacker, and from wanting to improve my tooling and improve my workflow, my high-level aims is to have better scalability. And that to me says I want to be more platform independent. I want to be working against a variety of platforms. I'll not have to change my tooling to work against new platforms as they come out or as they evolve. And I really want it to be easier and faster for me to develop those capabilities, to develop my attack logic, and to maintain them. They've got to work moving into the future. You've got a regression test. You've got to do QA. The other area is obviously stealth. I want, if any of my implants are detected, I want a reduction in attribution, and I want a reduction in the ability for my MO to leak. And obviously in the stealth, I want to try and avoid existing defenses. What are the current crop of defenses really looking at? Is there a nice way that we can kind of like step around that? So this talk's kind of been split into two halves, and I'm about on 20 minutes, so I'm doing pretty well. That first half is kind of setting the scene. Why have I even gone to the trouble of doing all the work, all the research that I've done, and write all the code that I've written? If you don't sit and have the pleasure of thinking about attack space all day like I do, some of that may not have made sense. So I didn't want to dive into a technical explanation of all this foo that I've done without giving you an idea of actually where was I coming at the problem from, why was I doing it. Now I am going to jump into that technical foo, and it's going to get a little bit more, I think, interesting. You guys might think complicated, I don't know. So, it would be great if I could have a single payload that just runs everywhere. That would be an ideal utopian situation for me. I could write a payload once and it will run on whatever target I come across. Well, it sounds kind of unrealistic, but there's a lot of there's a lot of technology which is really there in place to do that. Java, Python, Ruby, a lot of interpreted languages that really take that all the hard problems of platform-specific and OS-specific engineering and abstract it to a higher level. And they also help me address those problems of software engineering, rapidly turning around new code, making sure it's easy to QA, like all these nice things that the 20th century has given every other application developer. I want to bring into my attack application development, and I want to separate kind of what I'm doing it from why I'm doing it. And this is very much that I want to reduce my leakage of MO. So I can't stop you, if you have an instrumented system, I can't stop you from seeing what I've asked you to do. But what I can do is stop you from seeing why I've asked you to do it. So things like distributed systems can really help me split that question and the outcome. So that the decision point I can keep on my side, the action that comes from that decision point, it goes to your side. You're going to see that, but you're not going to know why, and you're not going to know what other possibilities may have been there. And it can also actually help with reducing the complexity of what you push out to a system, because I can keep some of the very complex things on my side. And the demo that we're going to see later is I'm keeping facial recognition on the kind of the server side, and not having to push it out into the client, which would be quite a complicated thing to do. It becomes very platform specific and has a lot of other ball ache with it. So keeping it on the server side has a lot of nice attributes. So if these are kind of my goals, how did I go about doing them? Well, I came up with a system, a proof of concept that's using kind of bytecode over the wire. Allows me to do cross-platform tasking. The Python VM are on Unix-like systems, OS X and Linux and whatnot. The VM's already there; it's part of the system. I can leverage that system utility to run my cross-platform code. For Windows, obviously, it doesn't ship with a Python VM, so we inject one. The point being, don't get too hung up on the Python-ness. Everything that we talk about today, you could go and implement in whatever your favorite interpreted language is. The point is that you're tasking in a platform-independent way. And we're not saying that we're, I'm trying to think of the best way to explain this. So a lot of people got confused at a different time when I was discussing this. They say, well, Metasploit is written in Ruby, which it is, but the post-exploitation capabilities, which are pushed over, they're P binaries or the Mako binaries or whatever the target is. So what we're talking about is the actual part that goes over the wire is platform independent. And the next graphic should help do that, show that difference. And it's a distributed architecture. The implant is a distributed architecture using RPC to split those decision points, and it allows some kind of quite funky dependency resolution to happen when the implant goes over, which we're going to discuss. So the difference I'm trying to pull out is the implant that goes over or the capabilities, the tasking that goes over is really executing in the runtime, in the VM, whatever you want to term those interpreted languages, rather than executing on the chip. So that bytecode is the same for all my targets. So I don't have to have 10 different versions of tasking to work on 10 different versions of the target, because as long as everybody's running Python, then they can execute my bytecode. So I've bitched on a little bit about Python. So we're going to have like a quick aside. I realize that not everyone is kind of a budding Pythonista. So we're going to have like 3 slides on Python internals 101, and then you'll all be up to speed and we'll be fine. So Python has bytecode. There's the thing that you write, which is the source code, and then it gets compiled to kind of an intermediate representation, which is bytecode. If you've ever seen any Python programs or whatever, the PYCs and the PYOs, which you might see popping up on disk, that's the bytecode. It's not really human readable. It's a pretty simple bytecode. There's about 125 mnemonics in it. But the key point that you should take away from this slide is that Python bytecode is portable. That's the whole point of it. So as long as the major and the minor versions are the same, so like Python 2.5, or everything's within the Python 2.5 branch or 2.6 branch, then it's guaranteed to be portable. You can actually play some games with only using subsets of code to ensure that it's portable across all versions of Python. It gets a little bit funky and we won't go there. But the point is, it doesn't matter what platform, what OS, what architecture, the same bytecode will run on any Python VM, as long as those versions are the same. Very useful property. So import hooks. Now you understand about bytecode. Python uses an import statement to do its dependency resolution. Essentially, you can split up your code into modules and packages, and you can say import ziplib, and it will grab that module and get all those dependencies for you. This whole import architecture is implemented through things called import hooks. Import hooks, you can write custom ones, and that really changes how the dependency resolution happens when you're asking Python to import stuff. It's all given out in excruciating detail in PEP 302. PEP, so like Python extension proposal extension of Python, I don't know, enhancement of Python extension enhancement proposal in there somewhere. And so it's detailed in there in very great detail, and it's a pain in the ass to write. They really are not nice things to play with. It's worth an entire talk just on itself on import hooks, and I'm sure none of you really care about Python that much. If you do, there's a fantastic talk by Brett Cannon, import this, that, and the other thing from one of the PyCons, and it really is a great talk. He goes through everything, so if this is something you're interested in, I would say that's your first reference, and he gives a bunch of other references so you can learn more about it. Python 3 reduced the pain because it provided a thing called importlib, a module called importlib that was written by Brett Cannon, and that makes writing custom import hooks much, much easier. Python 2 doesn't have that, and as Python 2 is the most widely deployed, used version of Python currently, it meant I had to go through the pain of writing my own import hooks. We look at an import hook, basically splits into 2 parts. There's a finder and there's a loader. The finder locates that bytecode, those blobs of precompiled intermediate language, finds where they are, grabs those bytes, and the loader, and that's pretty simple. It's not too difficult at all. The loader takes those bytes and kind of pushes them into the Python frame, fixes up, does a lot of kind of like housekeeping and metadata counting and things like that. Quite annoying, but the point being then, the frame from which you are executing has access to the bytecode that you've just imported. So you're just somehow getting bytecode from somewhere and pushing it into the current Python frame. That's all you need to know. So now we're going back to the regularly kind of scheduled broadcast, and we're going to hop into really how the implant that I created, this RPC implant, works. So the Python VM at the bottom, that's either the system Python VM that just comes as part of the operating system, or it's the injected Python VM if we're looking at Windows. And I said that, when we look at that picture, there was my little pony. Like, this is my pony. It's a bit less good looking than it was before, but this is my persistent code. It's the only part of the implant which is persistent. It's pure Python. It's just an event loop, nothing more. It literally sits in a circle. It reaches out to try and grab bytecode from some predetermined points over the wire, over SSL, pulls that bytecode down to stop bootstrapping. The thing that it bootstraps is the first import hook. So we're going to go through like a 2 or 3 stage bootstrap, but this stage 0 is the only thing which is persistent. It's got nothing that says anything about my goal for the attack. It's got nothing that has any capabilities. All it does is pull in a blob of bytecode, execute it. That blob of bytecode could be anything. In this case, it's the stage 1 import hook. And this import hook, a PEP 302 import hook, it just does a slightly bit more than stage 0. It's able to reach out and grab a whole zip of modules and packages. So a bigger bundle of bytecode, pulls it into memory, and imports it from memory. So it's a full import hook. Zip imports have actually been supported in Python 2.3. If people are sitting in the crowd being like, well, great, zip imports, they've been around forever. Well, they have. The problem is that the way that Python implements them, they have to be on the file system. You can only do a zip import from a local file system or from a mapped file system. I want to reduce my footprint. I want to have low detectability, and I want to execute only from memory. So, like I say, this is the persistent part that's on disk. Everything else just happens in memory. So I had to re-implement the zip file module, which is written in C, in pure Python, to be able to do this, to kind of screw things around, to be able to import a zip from memory. And a really bad graphic of importing a zip from memory. Stage 0 goes to stage 1, it kind of pulls in a zip over the wire. The zip goes into memory, it's expanded. You can tell it's expanded because the square's got bigger. And then there's the import hook with the finder and the loader kind of locates that in memory and loads it from memory, and then overwrites where it was in memory with a bunch of random data. And now all the Python code that was in that zip is accessible to me in the executing frame. Now the code that was in that zip is what we call stage 2, or what I call stage 2, and this is essentially the full implant. The basic system of the full implant. It's got the full RPC system in it, and it's got a RPC import hook. Now, this RPC import hook is really one of the key points, and if I was at a Python conference, I would probably want to talk about that a lot more. The point with the RPC import hook is when we're talking about we were resolving dependencies. I say import X, and then it goes off the file system, finds the bytecode for X, and pulls it in. With this RPC import hook, when there's an import X, or the bytecode representing an import X, now it reaches out over the wire to get that bytecode transparently. So you can have standardly written Python source code, compile it to the bytecode, you execute that bytecode, and then all the dependency resolution actually happens remotely. So this means that I don't have to rely on any non-standard or even any standard modules being existent on the system where the implant is, because they can all be pulled in over the wire, and it just means that I don't have to send massive chunks of data over initially, because everything is resolved on a kind of as-needed basis. It's fully symmetric RPC system. It's over SSL. It's actually based on a project called RPyC, written by a guy called Thomas Philibar. It's like a modified version of that to make it address my needs slightly better. But the full RPC system, again, allows me to really hammer down this point of splitting what I'm doing from why I'm doing it. Another really bad graphic. So this is more like how the RPC hook works. There's, on my server side, I've got kind of pre-compiled caches of all my tasks, and when any code executes on the implant side, any dependency that it needs to resolve, it reaches out over SSL and it kind of talks to the server and gets that thrown back, goes into memory, it's mapped into memory, it's loaded from memory, the memory is scrubbed. We do all our metadata markup and put stuff in the sysmodules table. Now that task is available to execute from the currently executing Python frame. So we've talked about this, the import hook, kind of the main loop, and I guess that's the kind of the core of the implant. It's pretty basic, but it means that we can, this main loop just kind of chunks through bytecode that's coming over the wire. But because of this remote dependency resolution, or the ability for this remote dependency resolution, I can send in very complex payloads in bytecode, but I haven't had to write like Python in any fancy way. It's just standard, normal, off-the-shelf Python, and all the dependency resolution happens remotely. I can keep everything server-side, everything executes in memory and then gets scrubbed. Now, this means, talking to some of my software engineering goals that we looked at earlier, it's much quicker for me to write new capabilities, target-specific capabilities in Python than it is in C or assembly. I used to work at Immunity. I've written a lot of MozDef code. I don't want to write a lot of MozDef code again. It's painful. So I much prefer to write standard Python rather than some kind of like bastard child of C and Python. MozDef very good for exploitation phase because exploitation phase is, by definition, platform specific. You've got to get pretty specific details if you're doing memory corruption in the exploitation phase. It's fine for that. Well, it's very good for that. For post-exploitation, I want to go to platform-independent methods, and writing in Python allows my team to write stuff much quicker. It's also much easier for me to debug and QA Python code than it is assembly or C. And this remote dependencies allows me to pull in modules that wouldn't necessarily be on the target system. So an example of like a task, one of these bytecode tasks that goes over, is the first task that's kicked off when the implant reaches back to the server. And this is to derive a unique identity for that target. Now, again, this is an area that I've kind of stood on a soapbox and moaned about before. Most attack frameworks use IP as their unique key, as their identifier for the systems which are being controlled. That's fine if you're like controlling maybe 10 systems over a LAN, which a lot of pen testing kind of does. But if you're doing a proper complex attack against real-world assets, IPs really don't work for all the reasons that IPs are bad unique keys in every other field of computing. NATing, private address ranges, all of these things, virtual systems where IP addresses can change very easily. So we derive a unique ID actually from the SM BIOS. There's a kind of 32-bit value in every BIOS. It is accessible via an API. So we've implemented in pure Python, a way to get that UUID in a cross-platform manner, just from Python space, which is pretty neat. But now we have a very, very strong unique key, and we can track that system even when it's moving between different networks, changing IP, anything like that. So it's a very, very useful unique key. If people are interested in that code, it's very welcome to have it. It's kind of funky to look at. So if you're into Python, it could be a good thing to view. The polling mechanism, again, another problem with a lot of kind of post-exploitation and shelling is people think shell code and they get a shell, and then they have a persistent connection, which is pretty damn obvious if you're looking at the wire. There's a persistent connection between the box that you're owning and whatever server you're owning it with. We didn't want that. The main loop here just uses a polling mechanism. So essentially, at server, you can queue up tasks based on UUID. So you're right, next time this implant checks in, these are the tasks that I want it to do. Implant checks in, bytecode goes over the wire, and it does it. You don't even really need to care what operating system that implant is running on. So it's polling, like random time intervals to make traffic analysis harder. As I said, nothing's touching disk. Everything just sits in memory, is executed from memory, and then is scrubbed from memory. To the extent that you can scrub Python memory, it's probably a different conversation that we need to have. Obviously, garbage collection in Python doesn't work like you would kind of imagine it from a secure perspective. So we go in and we do some funky stuff with C types to overwrite our own memory regions. We can get most things, not absolutely everything. But again, the point is making detection and analysis harder. So if the implant was detected on the box, and all your forensics guys come in and charge you like $6,000 an hour to sit in an image, a 200 gigabyte disk, then if they're doing memory analysis, then it should be much more difficult for them to see what was in memory. And a vast majority of forensics people, I'm sure if they saw Python bytecode in memory, wouldn't see it because all their tools are scanning for PEs anyway. So in this main loop, it's a cycle. It checks in with its UUID, and it returns any results from previous tasks with that check-in. And then the server side says, it's been chopped off the top. It did say server at the top. The server side says, all right, is there any tasks that are lined up for this UUID? If it is, it pushes bytecode over the wire. The initial bytecode executes. the RPC import hook is working, so when that bytecode executes, it reaches back and gets any dependencies as it needs. It queues up a new thread or a new task, depending whether you need synchronous or asynchronous execution. Gets the result, puts it in the cache, next check-in, the results go back, and they go back to the server. So it's a pretty simple loop. There's nothing too fancy there. These tasks that we spoke about, they're split into two parts. There's like the payload, which executes on the target. This is the kind of the what you do, and then there's the service, which is on the server side, and that kind of does the why you're doing it. So it processes the data that comes back from the target. And this executes on the server side, and it helps us do that split that we were looking for in trying to reduce our MO. If the payload is detected, then hopefully we can reduce the amount of insight that people can get into the goal that we're achieving. I've labored the point that everything is pure Python long enough, I think. And yeah, determination of the next step happens at the server, and that's kind of the key bit there. So there's two types of tasks. There's common tasks that are all pure Python. There's lots of tasks which can be dealt with very well in pure Python. Things like search a file system for private key.pem. Very implementable, pure Python, cross-platform. You don't need to do any system-specific stuff. Just that's the power of using the interpreted languages allows us to do this kind of stuff completely cross-platform. There's a balance to be made between kind of like stealth and efficiency, and make these trade-offs as is dependent on your target. If we're searching for secret.doc, we're leaking some MO there. But if we're just saying return every file name from the system to my server, then it's obviously a lot more noisy. So you need to balance kind of where you feel the defenses are, and make a judgment call on that. The other type of task is what's called a native task. Now, I've labored on about kind of we want to be completely platform independent, which would be lovely, but in reality there's a lot of tasking which you have to get down to the nuts and bolts of the environment that you're in. Ideally I'd want to get it to kind of like an 80-20 split. 20% of my things are native, 80% are common. But things like taking a screenshot or taking a webcam capture, turning on a microphone, anything like that, you're going to have to do some system-specific stuff. I can't do that from pure Python. It's just not going to happen. So there's a number of ways which you can kind of do native execution, like C types or PyObjective-C, subprocess. You can just call out to stuff, but all then tend to be quite forensically noisy. And obviously those native functions may actually be hooked on the operating system. They may be what are deemed sensitive functions, and people are watching for their usages or watching for usages that is abnormal. So I'd prefer to err away from that. And the solution, one solution, I'm sure there are others, is userland execution. At like a high level, userland execution allows you to replace or augment currently executing process image with a new process image from user space. So this means that I haven't had to drop anything onto disk and then use the normal kind of loader linker mechanisms to get that kind of binary into process space. Userland exec has been around for a long time. It's useful in a number of scenarios. I'm far from the inventor of it. It builds on kind of years of other people's research. The Gruck is the guy that's generally considered to be the father of it, but there's been incremental work by many people going back a long time, and yep. And one area that's probably worth noting out in some of these different userland exec is PyElf, written by Immunity, which allows you to inject an ELF binary into process space from pure Python. So for this demo, I've written PyMaco, which is an incredibly equivalent version that does it for OS X operating systems. This userland exec is kind of useful. It was done originally for anti-forensics reasons, for stealth. It's also really helpful if you ever find yourself in a system that's on a non-exec mount. So you've got binaries on the disk and you want to execute them, but it's non-exec mount, so you can't execute them. But you have an ability to kind of pull in bytes over the wire. And obviously it works very well for my situation where I'm in an interpreted language VM and I want to get native execution, but I don't want to touch disk. I have the ability now, the implant's set up, to read in Maco binary or ELF binary over the wire or PE binary over the wire, and then do userland execution to actually get that executing in my process space, which the Python VM is already executing in. So, this PyMac-O, which I've written, which is essentially the Mac equivalent of PyElf, allows me to, from Python space, inject real native binary. A nice side effect of it is it allows me to sidestep all the stuff that's in Mountain Lion for code signing and Gatekeeper and all that kind of stuff. So that's nice. I've got an image that just shows how easy it is. So we've got our implant. This is our bootstrapped implant. We send over a bytecode task. This bytecode task is really PyMac-O. So it executes, and then we send over some native binary data, and PyMac-O pops it into memory, and you've got a running process. It's really easy. So we're kind of coming up to the demo time, and I'm almost exactly on time, which has surprised me as much as anyone. For the demo, one of the things that we're going to inject is kind of a webcam capture ability. Everyone has kind of, you'll see iSite.bundle kind of cited everywhere, people demoing it, showing Macs being owned and stuff everywhere. The funny thing is it hasn't worked since like 64-bit Snow Leopard, and no one seems to have noticed. It relies on 32-bit QuickTime framework. That hasn't been around since 64-bit Snow Leopard, so it just fundamentally cannot work. So we wrote one using Qt-Kit that supports 32 and 64-bit, and I think it supports everything back to Tiger, but don't quote me on that. I'd have to check. So in the demo, we've kind of romped through and implant memory, kind of memory persistence, userland exec. We've gone through a bunch of stuff. So hopefully I'm going to show a demo that may kind of bring it all together. But before I just throw bytes at you, also my size looks awful. So we've got the Python VM. We're going to inject this stage 0 persistence. We're going to run an exploit, and via that exploit, doesn't matter what that exploit is, because we're talking about post-exploitation, we're going to get a stage 0 there. It's going to be executing. Once that stage 0 is there, it's going to reach out over the wire. It's going to do its stage 1. It's going to pull in this HTTP zip import hook. It's going to then bootstrap itself to the full RPC import hook. And then it's going to do its get system UUID to get its unique identity out of the BIOS. Once it's got that, it's going to be tasked. Obviously, I've set up the demo so that it's this UUID, you're going to inject this bundle. So it's going to send over a common task, which is the PyMac-O bundle, the injector, the userland space injector. And then PyMac-O is going to take that webcam capture bundle, inject it, execute, hopefully take a picture of my beautiful face this morning, and then the results are going to be pushed over to the server. Facial recognition is going to be done on the server, and then determination of next step can be taken from the server, because it can be like, this is Richard's computer, or this is Jason's computer, whoever it may be. If it's Jason's computer, obviously immediately RMRF it. So, before I jump into the demo, is there any questions, or is everybody really lost at 9:30 in the morning? Really lost at 9:30 in the morning? Awesome. Go for it.
Is there any reason why you didn't use MAC address instead of generating your own sysUUID?
Okay, so the question was, is there any reason that I didn't just use MAC address rather than sysUUID? Yes, thank you for the question. So yes, there was. So a lot of virtualization technologies can kind of share MAC addresses. There's a lot of server balancing technologies that can also share MAC addresses. And MAC address, while supposedly unique, can actually be fairly easily changed. Now, is someone spoofing a MAC address that's not, you could augment your operating system so that the value I get back out of sysUUID is spoofed, but it's significantly more difficult and happens less often. There's lots of legitimate reasons for changing your MAC address. There's very few reasons for changing sysUUID, so I just found it was a better unique key. But no, thank you for the question. So, demo time. So this is where everything goes horribly wrong, I expect. So just to explain the demo, just to make things more or less likely to work, I'm working off two systems. So there's this system here. It's joined to this one by a wire. This one is the target. This one is the server. What you can see on this screen is me VNC'd into this one, so I can try and all fit it onto one screen. Obviously, that's not working out too well. Just want to kind of. So the target is standard Mountain Lion install. Just here to this is just to show that the standard kind of configuration with Gatekeeper, just to show the process injection working, kind of the value that has at sidestepping Gatekeeper. And this is this is the server side like all the best attack tools, it's just command line and very, very cryptic. So start with the bootstrap server for the stage 1 to stage 2 grab, and then we're going to start up the implant server. Again, very, very interesting output. So this is on our target. We send in a special, special PDF offer. Obviously, we all know that if you open a PDF, you get owned. So we open the PDF. You definitely are not getting owned while you're reading the Comic Sans. But if we look here, there's been a callback. Stage 1, stage 2 bootstrap has happened. I'm going to try and get my face in front, and we can see all. This is all the kind of remote dependency resolution happening. This string here is the like the SM BIOS, which is the unique key that's come out of the BIOS, so we know which system we're attacking. And this is all that going back and forth, dependencies, loading bytecode, or no bytecode, depending on what the request was. And where does it? Face is detected. Awesome. So we actually so the userland exec happened. The bundle was injected. That's why I was holding this here, so it could get a picture of my face, and it looked like faces were detected. So let me just pull up the little cache. So here's me looking fantastic, so that's the snap that came over, and then this is kind of thing. The facial recognition works. So yeah, I've got a big pink square around my head. That's definitely me. But all that happened on server side, so we won't have to do facial recognition on the implant side. Reduce the complexity of our implant a very great deal. So as demos go, it's probably like the least exciting, but at least you got to see a cat. So and it worked. So it's always a bonus. So I'm going to kill the server and then step back. I've got 5 minutes to spare and 2 slides to go, so I am pretty impressed with myself. So some lesson there. Don't be a smug bastard. We'll just do it from here. So kind of like some technical takeaways. It's my belief, honestly, that the current post-exploitation tooling and approaches don't scale well for anything other than very small amounts of very basic pen testing that doesn't have that long tail of the attack process. You exploit, you kind of pop a box, or you pop a calculator, and maybe load an interpreter, whatever it is, but you're not doing that whole long tail that we had on the attack timeline. Also, baking in capabilities just leaks your intent and gets all the AV industry having a race to write more blogs about your implant. It's probably not what you want. Interpreted languages can really help us with this scalability problem. Scalability both platform-wise and development-wise, our development processes. And distributed architectures can help us with the ability to split what we're doing from why we're doing it, separate our action from our reason. Lots of technologies, both interpreted language and distributed architectures, can kind of be put in place. My demonstration was with Python and RPC, but you can make an equivalent implant with whatever it is that floats your boat. So there were the technical takeaways. Kind of calls to action, which tends to be like more the higher level takeaways. I would probably, some of you in this room are kind of providers, pen testers, red teams, whatever it may be. I would really ask you, don't let the tool sets limit your ability to attack. And what I've seen time and again when I've spoken to pen testers and attack teams is really people blaming the tools, and it's very easy to do, and I've done exactly the same. Some of the tools suck. But rather than just bitch about them, innovate, change, identify the problems, critique what it is, and really expand them. And just think back to that line where we're really only addressing the kind of the first quarter of the line, and there's so much beyond the exploitation that we're really not addressing well. So I would call to all my kind of fellow attack technology people to really kind of up the game and make things better. And the people that are kind of paying me to develop all this attack technology, paying us to do the pen tests, I'm really going to understand the difference and the difference in value between pen test and attack teaming or red teaming or wherever you want to call it. I'm not saying pen test has no value, because it absolutely does, but it's different value than attack teaming, and understanding that difference kind of really sets you apart and your company apart in having kind of a very mature understanding of security. So I am done. Any questions? I think there's a microphone.
So you've clearly got quite a sophisticated kind of attack framework, which I guess by definition is also a pretty good remote access and administration framework. Now, as someone who's on the defensive side, if you're using this technology, I'd be quite worried about the actual security of your solution. It's a large framework. There's lots of complexity there, lots of things to go wrong. How much does that concern you, and what's your answer to that if I'm worried that someone's going to subvert one of your components to actually, the bad guys are going to get in through your system?
It's a great question. And I would say as part of the process of those more complex attacks that kind of I spoke about at the start, and that they kind of hinge on having these more complex capabilities. Yes, it is absolutely a concern. The last thing that I'd want to do is kind of be working for a customer, attacking them, and actually, it was our backdoor that was used to really, cause them, significant damage. Certainly wouldn't. I doubt they would come back to us for another contract. So yeah, absolutely great question. The technology that we're talking about there, this is kind of proof of concept, some speculative research stuff. So this would not be anything that I would the Python thing that I just shown would not be something that I have deployed, kind of in that form on a customer server, because it really, it's not battle hardened enough for those exact reasons. To your kind of the meta point from your question, which was, the risk, the inherent risk of doing more complex attack, kind of attack simulation or whatever you want to call it against a customer, and could that open them up to significant risk from real attack? Yes, I think there's always that risk that's going to be there. And that's when we work with customers. We work with ones that are pretty advanced, pretty secure anyway. They've gone through all the normal standard kind of pen testing routines, and then kind of come to us and have like an extra thing put on top. And they understand that risk, but they see the value as outweighing that risk. So the risk is there, absolutely. We can try and minimize it, but I'd say it would be disingenuous of me to say that it could be removed entirely. Any other questions? Going once. People are walking out. Thank you very much.